Here is a mini lecture for Pre-Calc, and it's section 3.1.1. This comes at the very end of your classwork. This is on page 117, and it's partial fraction decomposition. So I don't think you've seen this before. So this is what we do when we want to take a fraction apart. Like, let's look at this thing backwards. Let's say somebody asked me to add these two fractions together. Wouldn't I have to get a common denominator and like multiply the top and the bottom of the first fraction by a giant 1, and I'd have to do the same for the second fraction, and I'd have to do a lot of math, and I would end up being able to write these two fractions over a common denominator, which would actually end up looking like this. That's kind of what you know how to do that, like how to add two separate fractions with the unlike denominators by getting a common denominator, and then you can add them together. But sometimes it is necessary to pull them back apart again. So if you have, let's say you don't know what they were before you added them together, and let's say you're given this and you're asked to decompose this. That means that you're being asked to find out which two fractions got added together to make that. So the easiest way to do it is to break it apart into two fractions. We have this factored, it's factored on the bottom, so you do one fraction for the first factor and another fraction for the second factor. Now you can read along in your book on problem 3-10, and it'll take you through step by step. And I'm going to also kind of take you through step by step, but I wanted you to see why we would even want to do such a thing. So let's say someone asked you to decompose this fraction. What they're asking you is to write it as two separate fractions, and we want there to be just a constant on the top of each. Like, because I already did the problem. I already know that this one's 7 over that, and this one's 4 over x plus 1. I already know what it is, but pretend you don't know. So here's how you'd go about finding out. What you would do, you can't really see this, is you would multiply through by, that says 2x plus 3 times x plus 1. I'm multiplying through to each term, trying to get rid of the denominators. So when I multiply this first fraction by the 2x plus 3 and the x plus 1, let's get this closer so you can read it. When I multiply the first fraction, we have a cancellation, and you just end up with 15x plus 19. And then when I multiply the second fraction, the 2x plus 3 cancels out with the other 2x plus 3, and I end up with x plus 1 times a. And when I multiply this fraction by, see, I have an equal sign, so I don't have to use a giant 1. I'm just multiplying both sides of the equation by 2x plus 3 times x plus 1. So when I multiply the last fraction by 2x plus 3 times x plus 1, the x plus 1s are going to cancel out, and I'm going to end up with b times 2x plus 3. Then the next step is I'm going to solve this thing by equating some exponents. Sorry, not exponents, coefficients. I'm going to equate the coefficients. So what I want to do is kind of get the x terms more together, so I'm going to distribute this out. So I'm just simply distributing the a and the b, and you can see my work there. And then I'm going to rearrange them so that all the x terms are together. So I just moved the x terms so that they're close to each other, and that's all I've done, just rearranging it. And then here, now that I have the x terms both together, I'm going to factor out the x. So I haven't done anything over on the left-hand side yet. I factored out an x, and then this might not jump out at you, but on the left-hand side, I have 15 times x, and on the right-hand side, I have a plus 2b times x. These are both coefficients of x. And this, since there's no x, this has got to be the constant, and the constant's got to equal 19. So that's called equating the coefficients. So, and that's, I just wrote it all out right here. I wrote that let me push autofocus. I wrote that the coefficient of x equals the coefficient of x. So that's how I'm able to write 15 equals the a plus 2b. Okay, and then the constants, these two constants must be equal to each other. So I wrote that 19 was equal to a plus 3b. Okay, so now I've got two equations. They have a and b in them. So I can use substitution, elimination, equal values, whatever. I can solve them as a system of equations. So I'm going to go ahead and use elimination, because I think the a's will cancel out. So I just subtracted this blue equation from the red equation. So 19 minus 15 is 4. A minus a canceled out. 3 minus 2 is 1b. So now I know b. b is 4. We already knew that because I showed you in the beginning of the video, but there's my b. And then I can plug b in to find a. So I just plugged b right in here. So I've got, well, I plugged it right here. 15 equals a plus 2 times 4. So a must equal 7. So now I know that what a and b equal. So then I can just go ahead and, now we're right back here. I just plugged in, because remember we had a and b. So I just plugged in, a was 7, so I plugged in the 7, and b was 4, so I plugged in the 4. Now, I'm checking it. So you guys already know how to check it, because that's what we've kind of been working on, even in chapter 1 a little bit. Multiply by a giant 1, right? Multiply them. And this is just showing me getting a common denominator of x plus 1 times 2x plus 3. And then I can combine like terms over here, and I end up back where I started. So you would do this maybe, especially if you're trying to, look up. Well, actually, you can do this for rational functions, to put them in that form that we like, the graphing form. But also, you might want to do this later in calculus, because maybe you're trying to take a derivative or something, and you need to, or integrate something, and you need it to be in a certain form. Like, you can't do it when it's like this, so you have to pull it apart. So there you have it.